much. And I would also like to thank the organizers for giving me the opportunity to speak today. And I want to speak about some recent progress on the nonlinear Schrödinger equation, which is posed on a compact three-dimensional manifold. And today I want to talk, first I want to introduce the equation and some known results. And then I want to convince you that it's quite important to study a certain trilinear Strichartz estimate. And finally, we are going to prove the trilinear Strichartz estimate in 2 cases. And let's start with the introduction. So this is the equation that we consider. It's the nonlinear Schrödinger equation, but this time it's posed on a 3-dimensional compact smooth Riemannian manifold without boundary. And here, Laplace G is the Laplace-Beltrami operator, and we consider the quintic equation, so the nonlinearity is u, the modulus of u to the power of 4 times u. And we have initial data in H1. And then there are several questions. The first one that I want to ask is there a global well-postedness for small initial data for initial data phi in H1? The second one that I want to ask is, since we are on a compact domain, every constant function is a solution to the linear equation. And hence, the well-known dispersive estimate in the R3 case is not true anymore. So this equation, this inequality cannot hold. So what do Strichartz estimates look like? What can we expect? And the last question that I want to ask is there any general strategy that has been developed in the last few years how we can prove some global or local well-postedness results? And first of all, there are 2 conserved quantities. The first one is the mass, which is basically just the L2 norm squared. Then we also have the energy, which is basically the H.1 norm squared plus the L6 norm. And if we consider the quintic nonlinear Schrödinger equation on R3, we have a scaling. The scaling looks like lambda to the power of 1/2 times u of lambda squared t and lambda x. So H1 in R3 is the scale invariant space. And also the energy is scale invariant. And that's the reason why we call the NLS, as it was stated on the first slide, the energy critical nonlinear Schrödinger equation. And as can be seen by arguments, I think they were spelled out in the paper of Herta, Taro, and Svetkov in 2011. If we are in the energy space, the local well-postedness result immediately implies the global well-postedness result for small initial data in H1. Now, I want to talk about the linear evolution operator. Since we are on a compact manifold, the spectrum of the Laplace operator is discrete, right? So we can list the eigenvalues like this. 0 is equal to lambda 0 squared, which is less than lambda 1 squared, and so on. And now I want to show you some examples. So the first one is the rational torus. And here, the eigenvalues are exactly n, the modulus of n squared, where n is a 3-dimensional integer. So we have n1 squared plus n2 squared plus n3 squared. And this is almost the same as for the irrational torus, where we have some real numbers, lambda 1, lambda 2, lambda 3. It's positive, they are positive real numbers. And we only multiply each of these terms by this lambda, by this alpha 1, respectively alpha 2 and alpha 3. In the case S cross S2, the situation is quite similar. We have also the modulus of n squared, but this time n is a 2-dimensional variable only, okay? But it's the same structure. It's modulus of n squared. And on the 3-dimensional sphere, it's almost the same. It's n squared, where n is just the an integer or a positive integer. So we have some kind of, they have some kind of similar structure of the eigenvalues. Okay, now we want to denote hk by the spectral projector on the eigenspaces ek, which correspond to the eigenvalue lambda k squared. And then we have an orthogonal decomposition. L can be decomposed into the sum of the eigenspaces. And hence we can write the, and this is what I want to show you now, is hence we can write the linear evolution operator as the sum over all the eigenvalues, and then we have e to the I t times the eigenvalue, and we multiply this by the spectral projector of the initial data. And also I want to define, or I briefly want to mention how we want to define the HS norm, and it's just 1 minus the Laplacian to the power of s over 2 of L2, endowed with the norm where we sum over all eigenvalues, and we have lambda k in these Japanese brackets to the power of 2s times the L2 norm of hkf squared. And now let me sum up the known results. The nonlinear Schrödinger equation, as posed on the first slide, is locally well posed in H1 and also globally well posed for small initial data in 4 cases. The first case, and this was the first result in this line of research, was by Hertetaro and Swetkov in 2011. It's the 3-dimensional torus. The second one is was obtained by Sebastian Herr in 2013, and it's S3, so the 3-dimensional sphere, or even more general, Sol manifolds. But from now on, we will only talk about S3. Okay. Then in 2014, so this year, at the beginning of this year, these local and global well-posedness results have been proved for the irrational torus, and recently also on the product of 2 spheres, so S cross S2, by Sebastian Herr and myself. And there have been previous results, previous subcritical results. The first one was a very important work of Jean Bourgain in 1903 about the 3-dimensional torus. And there he proved subcritical well-posedness. And a nice work of Bourgerat and Swetkov proved the subcritical result for S3 and S cross S2. And also by Gu, Wu, and Wang last year, they had a result that proved subcritical well-posedness for the irrational torus. And these results up here have been extended to global well-posedness in the critical case, even for large data, by Benoit Posada and Alex Ionescu on the 3-dimensional torus in 2012, and on the 3-dimensional sphere by Ionescu, Posada, and Wang this year. And there is also an ill-posedness result. Laurent Thoman showed in 2008 that if M is analytic and we're in the subcritical regime, so S is less than 1, then we cannot expect well-posedness. And there are other critical problems in 3 dimension has been studied by Wang and Gu or Wang, and they consider the 3-dimensional torus and the irrational torus, but with other nonlinearities, with higher nonlinearities, and they proved well-posedness in the scaling critical space. Now let's talk about the Strichartz estimates. There's a very nice result due to Bourgerat and Swetkov, where they proved a Strichartz estimate for every 3-dimensional compact manifold. And if P is larger than 2 and Q is less than infinity, and they have this, and they have these are admissible conditions, then we can prove the following, or then they prove the following estimate. The linear evolution in LP in time and in LQ in X is bounded by the initial data in H1 over P. However, there's one drawback of this estimate. It's not scale invariant. It would be scale invariant if we have L2 on the right-hand side. And hence, this equation is not useful for the critical well-posedness study, unfortunately. Okay, but there have been improvements in Strichartz estimates in our 4 considered cases. So, first of all, if n is a dyadic number which is greater or equal to 1, and if we are on the if we are on the torus, the irrational torus S cross S2 or S3, then we can prove this kind of Strichartz estimate where Pn is the projector on frequencies of size n, and then we get a factor which is scale invariant n to the power of 3 half minus 5 over P. And if we look at the range of P in the several cases, then we see that on the torus and on the Sol manifolds, or S3, P can be bigger than 4. It's true for every P larger than 4. However, on the irrational torus, it's only 16 over 3. And even worse, on S cross S2, we only have the result that P is greater or equal to 6. Let me just briefly mention in this, at this point that, in fact, there is an improvement here. So Bourgain proved something more, but we will come to this later. I just wanted to state one nice theorem where we have the same integration in P in time and in X. So if you wonder why I didn't mention this, we will make use of it later. Okay, and now, why does this Strichartz estimate still do not suffice to prove well-posedness in the critical space? If we want to argue by the contraction mapping principle, then what we do is we have, since we have a quintic nonlinearity, we have 5 terms. By duality, we get another term, so we have 6 terms. And so what we are shooting for is an L6 estimate, right? And we have to bound this integral over 6 functions by a factor of frequencies, but this bound should not depend on the highest frequency with a positive power. And if we go back here, we see that we cannot avoid getting the highest frequency into the game without, if we just use the linear Strichartz estimates. So we have to get a new idea what we can do. And one way out is, and I think this was used also the first time, I think, by Burgera and Swetkov. Maybe I'm wrong here, but I think it's the case. And we want to prove critical trilinear estimates. And the starting point is as follows. In all those 4 cases, we want to improve the known L6 estimate, which looks like this, by using almost orthogonality in space and in time. And then we can prove the following estimates in every of these 4 cases. And for example, for the T3 case, it was done by Hertataro and Swetkov, on the irrational tools by myself, on S cross S2 by Sebastian Herr and myself, and on Sol manifolds by Sebastian Herr. So why is it an improvement? We have 3 functions over here, the product of 3 functions in L2. And so what we get is we get one of these factors. And what is very important here is we have only a dependence on the lowest frequency, on the second lowest frequency, and we do have a dependence on the highest frequency, but we gain something. So this is a negative power, and this is very crucial. Yeah? So if you don't think about, if you just forget about this term, then we have a scaling invariant estimate with these terms over here, and these terms, but we get a little factor, we gain a little factor of n1. And this is the main advantage. Yeah? And this trilinear estimate implies local well-posedness and global well-posedness for small initial data. And this is true for every three-dimensional smooth manifold. And this was spelled out in the paper of Herr and myself, but I think it goes back to the iteration spaces that was first introduced by Herr, Tataru, and Svetkov. So this is the main ingredient. In this paper, you will just find a remark how this exactly works, but the main work was done over here. So this is a remarkable work. Okay, and now I want to convince you that gaining this trilinear Strichartz estimate is not very complicated. The basics idea are very simple. And okay, so let's do this. First, let's recall what the linear evolution looks like. And now in our forecast, it looks explicitly like this. So what we have in common here is like this. What we have in common, we have t times the modulus of n squared, something similar here, something similar here, and something similar here. So this do all these estimates, all these linear evolutions have in common. And then on the torus, we have this factor here, which basically comes from the inverse Fourier transform. And of course, we have something similar on the irrational torus, where x dot alpha n is defined by this sum. And now on the product of sphere case, so S cross S2, we want to write x as theta, comma omega, where theta is in S, which is of course equal to the torus, and omega is in S2. So from this one-dimensional torus, we get the same structure. We get the same e to the theta times n1, where n1 is the first component of n. And this is the spectral this is the projector on spherical harmonics of degree n2 in 2 dimensions. And theta n1 is just the n1 Fourier coefficient of phi in the torus component. And on S3, we have the same. We have the spectral, the projector on spherical harmonics of degree n in 3 dimensions this time. And since we have no torus component at all, we don't have this kind of factor here. We only have the time in the exponential function. So there's a lot in common, but it's not exactly the same, right? However, if we look at this, it becomes clear that in order to gain any Strichartz estimates, we have to deal with LP norms of exponential sums. And this is one very crucial ingredient. And fortunately, there are some exponential sums that we can use. The first one I want to mention is due to Bourgain in 1890. If p is larger than 4 and we have any interval of size of length at most n, and if we sum over all over all integer numbers in this interval, and we sum an times e to the it n squared, and measure it only in t, so LP in t, then we get a loss of n to the power of 1/2 minus 2 over p. And there's another version of it. As you can see here, for the torus, we get another term here, right? We get another exponential term here. And so Bourgain introduced in 1993 another estimate, which is true in more dimensions, but I just stated it in dimension 2 and 3. If p is larger than 4, and instead of an interval, we consider a cube with side lengths n, or at most n, and we sum over all the lattice points in this cube, then we can estimate this exponential sum by n to the d over 2 minus d plus 2 over p. And maybe let me just copy this in the case d equals 2 for later references. So we have the sum where we sum over all the integer numbers in C, a n e to the I n times x, e to the it n squared. And this time we integrate over t and x, and this is less or equal to, in 2 dimensions, it's n1 minus 4 over p. Okay, and now these estimates appear in the proof of the Strichartz estimates in every of those 4 cases. So either of these estimates appear in the proof of the Strichartz estimates in either in these 4 cases. So it's really essential. Okay, and now let us start to prove the trilinear estimates for the irrational torus. And now I really want to convince you that it's quite an easy strategy up to some minor technical issues. Okay? So this is what we want to prove. And again, recall that n1 is the highest frequency and n3 is the lowest frequency. Now, first, by almost orthogonality in space and time, the situation looks as follows. First, the spectral projector Pn1 tells us that the function e to the I delta phi 1 is located in an annulus of a very big size, of size n1 actually. And this is in 3 dimensions, so I don't know, it's a 3-dimensional annulus, I can't draw it, okay? But now, by orthogonality, almost orthogonality in time, it tells us that we only have to consider those frequencies located in a box of size n2. Again, in maybe I can try to draw it now, in 3 dimensions. And even better, the almost orthogonality in time allows us, or tells us that it suffices only to consider a very small rectangle in here, any arbitrary rectangle with this size. So I hope I'm not very good in drawing, but I hope it's getting clear what I mean. So, and the rectangle has the following properties. This length is n2, this length is n2, and this size is only m, which is the maximum over n2 squared over n1 and 1. Okay? And actually, this is the point where we get the scaling critical part of this estimate. So the n3 over n1 term, we gain it from this, and this is responsible for the subcritical part. It's this plus 1 over n2. Okay, so we only have to consider this rectangle. Now, what we want to do is we want to prove a Strichartz estimate that only takes into account where or how much the frequencies vary, and not takes into account where how big the absolute size of the frequency is. So it doesn't matter. We have one estimate, this one, which was proved by Bourgain, which is true for any of these cubes, no matter where it's located. Now, whether it's located on high frequencies or low frequencies, or I don't know. Huh? So this is one main point. And this was proved by Bourgain in 2007. And for p greater than 16 over 3, and this time this is the improvement I talked about earlier. In fact, it suffices to measure the space variable in L4. Then we get this kind of estimate. Okay. This is for the irrational torus, even. For the rational torus, we have there's even more better estimate. And so this is one point. There's one obstruction though. We haven't used this additional smallness condition yet. So we were not able, and it's very hard for small p to make use of this additional smallness condition. But fortunately, this is very easy to to use at the L-infinity estimate. If we want to prove the L-infinity estimate, then we just go to the Fourier side, use Cauchy-Schwarz once, and then we are left with counting points in this area. Well, and counting points in this area is very easy, since we have a rectangle of size n2 times n2 times m. It's only n2 squared times m. And since we use Cauchy-Schwarz, we have the square root of it, so we end up with this. So it's really easy. So there's a way, if we now interpolate these two estimates, we have an LP estimate for small p with a little influence of this small size m. And this is the main point. Okay, now let's start proving the trilinear estimate. So as I told you earlier, it suffices to consider this rectangle, yeah. And now the game is always as follows. We want to have a loss on the lowest frequency that is as high as possible. So we want to put this, the low frequency term, in LP with very large p. That means that all the other terms, the high frequency terms, go into LP with low p. Okay, let's see how low it can be. It can be 16 over 3 plus and L4. But we want to interpolate a little with this L-infinity estimate. So we also take L4 plus here. Then we do the same with the second term, although interpolation with this estimate does not give anything. And okay, then we are left with L8 and L-infinity minus. Okay, now let's see what we get. From this estimate, we get, if we choose p equal to 16 over 3 here, then we get 3 over 8. And since we interpolated with 3, with this estimate, then we get a little influence, a little factor of m. For the second one, it's the same. So we get the same factor n2 to 3 over 8 plus, but this time, of course, there's no additional smallness condition here. And for the last term, we have L8 and L-infinity. So first we use Sobolev's inequality to go from L-infinity in space to L4 in space. In 3 dimensions, this gives exactly 3 over 4. Now, we want to use this estimate. So p is equal to 8, almost. And then we have 3/4 minus 2 over 8, which is 1/2 minus. And that's all. Now, let's do the math. 3 over 8 plus 3 over 8 is 3/4. And 3/4 plus 1/2 is 5 over 2. 5 over 4, I'm sorry. And so, in the end, we end up with this term, with these two terms, and this basically comes from m. So this is all. It's very easy, isn't it? Okay. Now, things are getting a little bit more complicated here, but the general structure, again, the general structure is the same. We have the same 4 points. First, almost orthogonality, space and time. Then we want to prove an appropriate LP estimate for small p, where we don't make use of any of this time orthogonality like here. No, the smallness condition that comes from time orthogonality. Then the first step, again, is an L-infinity estimate, where it's very easy to make use of this smallness condition, and then we put everything together. Okay? So let's start with the first step. Now, again, we neglect these linear terms in lambda k squared, so for the eigenvalues. It doesn't matter at all. And this time, the situation is a little bit different. N, so the eigenvalues are just, this time it's only 2-dimensional. So again, we have this very big annulus N1. And now, this looks N1. And now, time orthogonality allows us to consider only frequencies that are located in a cube, 2-dimensional cube of size n2. And then, by time orthogonality, it suffices even to consider something like this, so an annulus, where this size is again, m, which is the maximum of n2 squared over n1 and 1. Okay? And now, let's try to prove the LP estimate for small p. At the moment, it's not quite clear why we want to prove this kind of estimate, but it will become clear later. But this is the LP estimate, which will work in the end. So this exponential sum estimate is what we want to prove. And now if we take a look at it, it's almost the same as the exponential sum estimate by Bourgain. Yeah? If we compare it, this is a two-dimensional cube, this is a two-dimensional cube, then we have this vector an, but the only difference is here. This time, theta, the s component, is only one-dimensional. And this is different in here. Here it was two-dimensional, okay? But then again, okay, up to a sign here, but the sign doesn't matter. Here we have exactly the same. And now we want to prove, I want you to show how to prove this exponential sum estimate. And it's surprisingly easy. So this is what we want to prove, what I stated on the slide before. And now we already noticed that it's almost the same, except of the fact that one variable is missing here. Is missing there, sorry. So what can we do? We can introduce another variable. It's very easy. So if we introduce the variable nu, and if we set nu equal to 0 on the right-hand side, then it's exactly what's written on the left-hand side. So it's clear if we take the supremum nu over 0 to 2 pi, then it's clear that this is bigger. Quite easy. Now we have an L infinity norm outside in nu. What we want to do is we want to use Minkowski's inequality to pull this L infinity norm inside. And then it looks like this. But we're still not here. So what we want to have is we want to have not the L infinity norm in nu, we want to have the LP norm in nu. Okay, but this is only an application of Sobolev's estimate. And we get by Sobolev's estimate in one dimension from L infinity to LP, we get n to the 1 over p. And now we're exactly in the situation of this exponential sum estimate by Bourgain. And we have, this gives n to the 1 minus 4 over p plus 1 over p, and we end up with what I claim to be true, n to the 1 minus 3p. Very easy trick, but surprisingly powerful somehow. I don't know. Okay, now that we get the LP estimate for small p, we want also to get an L infinity estimate. But again, it's an exponential sum like this. And remember, S is defined as this set. This is S. And again, we just go to the Fourier side, apply Cauchy-Schwarz, and then we just count the lattice points in here. And maybe it's a little bit more tricky because it's curved, because it's not a rectangle. But just some heuristics. This length is almost the same as n2, right? Because we are in a box or in a cube with side length n2. And this width is m. So it's almost the same. It's, roughly speaking, it's almost the same than a rectangle of the size m times n2. And this is what we get here. Again, since we used Cauchy-Schwarz, we have to take the square root. Huh? Okay, this point maybe is a little bit more tricky, but it's not very complicated at all. Huh? Okay, now it's getting a little bit more, yeah, it's hard to keep the overview, but the idea is, again, very simple. So first I want to recall this linear evolution. The linear evolution on S cross S2 looks exactly like this. And I also want to recall a trilinear spectral cluster estimate of Bourg-Gérard and Swetkov. And what is it? It's like if we multiply the, if we take three functions, phi1, phi2, phi3, and if we project it onto spherical harmonics of degree n1, n2, and n3, and if we multiply then in 2 dimensions, so on S2, then this can be estimated by n2 times n3 to the power of 1/4. And what's the important point here? The important point again is we don't lose on the highest frequency n1 here. So this is one very important step in proving this result. We don't, if we take the trilinear spectral cluster estimate, then we don't lose on the highest frequency. Okay, and now, as I said, it's going to be a little bit, it's hard to keep the overview, but I want to, still the idea is very easy. So in the first step, what we do is we have the product of 3 times this sum, right? And what we want to do is, first, we have the L2 norm outside, and now we want to pull it inside so that we can use this trilinear spectral cluster estimate. Of course, if we do it naively, then we will lose this oscillatory factors, and we don't want to do that because then we are out of the game. But there was a very nice trick used in Burg-Gerard and Svetkov's paper. If we go to the Fourier side, then these exponential terms are just, these conditions are just hidden in a sum in some sense, and then we can pull the norm inside without losing these oscillations. Then we end up with this kind of estimate. We apply it, which leads to this factor, and then we are left up with the product of the L2 norms. And this is exactly my coefficient sequence here. Okay? And now we go back from the Fourier space to the physical space, and again we have something which looks like an exponential sum estimate. And this is why we considered this weird exponential sum estimate before. So this is why we considered it in point 2 and 3, in step 2 and 3. Okay? So we have this. We have the product of 3 exponential terms in L2. And again, the low frequency term should go to an LP space with very large p, and the other terms, the high frequency terms, to an LP space with very low p. So let's see how low it can be. As we proved here, as we proved before, p has to be bigger than 4, so it goes to L4 plus. The high frequency term, the second highest frequency term, and the low frequency term then can go to L infinity. Okay, this is what we just saw before. So L4, L4, and L infinity. And now I want you to recall the 2 steps, the 2 exponential sum estimates that we proved before. And here, for the first term, let's see what we get. So this is this factor here from the spectral cluster estimate. For this factor, we get n2 to the, and now let's see here, if we plug in 4 here, then we are left with 1/4, so 1/4 plus. And since we interpolate again between those 2 estimates, we get a little factor of n again. So it's very simple again. Just use the strength of the L infinity norm. And we do the same here. So this gives again n2 to the power of 1/4. And the last term, if we plug in L infinity here, then we see that it's almost that it's 1, but we don't have L infinity here. We have L infinity minus, so we end up with n3 1 minus. Okay, and now let's do the math again. So we have n2 1/4, 1/2 in total, and then 3/4 in total, and n3 1/4 plus 1 is 5/4, and again we have this kind of estimate. So it's, again, the basic idea is very easy. And I hope I was able to convince you that I'm not lying in this point. Of course, there are some technical difficulties and so, but the basic idea is really simple. And I somehow hope that this idea can work even in a more general setting. It seems to be quite a good idea, because for small p, if we want to have Strichartz estimates for small p, it's very hard to make use of I tried it for a long time to make use of this additional smallness condition. So why should we do that? Why not just take this by orthogonality in space and time? Why not just take the cube with side lengths of the second highest frequency? Then we already have no influence of the highest frequency anymore. And then, if we want to get a slightly better estimate with a little gain in N1, then we just use the stronger almost orthogonality in time, which gives another restriction like this. And for the L infinity estimate, it's very easy to use. And we do not lose much as we interpolate with this L infinity estimate. Okay? And of course, the question also raises, is this kind of trilinear estimate that we proved now for the irrational torus and for S cross S2, is it also true in a more general setting? I have no idea. I mean, the strategy looks very good, I think, but what does prevent us from proving it? Well, it's quite easy. As you remember, on the linear evolution we have e to the t lambda k squared. And for a general manifold, we have no idea what this could look like. And this makes it really hard to prove anything. Till now, we only used some kind of quadratic structure here of the eigenvalues. But for a general eigenvalue, I have absolutely no idea. And maybe I've just a guess, but maybe it requires also a more general kind of exponential sum estimates. These exponential sum estimates are a little bit too concrete, even for the irrational torus. This do not work. One has to play around a little, and you will find it in the paper of Bourgain from 2007, I think. And even for the irrational torus, this specific kind of exponential sum estimate do not work. One has to go back to this one that is only in time, not in space. But still, the question is, are these exponential sum estimates true in a more general setting? Yeah, and that's all I wanted to say today. So thank you very much for your attention. Which result? Wait, let me. Yeah, it's basically like the irrational torus is defined by. So TD alpha, or T3 alpha, is nothing else but. So alpha is the only restriction is that it's less than that is bigger than 0, and yeah, less than infinity, of course, and that's all. So it's every rectangular irrational. Well, what do they look like? I have no idea. Okay. Well, it depends a little. So the idea is, if it's only a slight perturbation of, if the eigenvalues are only slightly perturbed from the original one, from n squared, then it's no problem. But to be honest, I have no idea what the eigenvalues then look like. But there is some room for improvement. So you can play around a little with this. If you take a look at the paper of Bourgain in 2007, then it becomes clear that there is some freedom. You can change this a little bit, but not too much, but a little bit, and maybe this covers also this case. But I can't tell. I really think that this will work. but not with the methods I presented. I think you have to use methods that were used by Bourgain in this paper. Then you can do it. There's a small remark that you can prove the S cross S2 case also with the same methods as it was done by Bourgain. And if you do that, you do not rely so much on this precise, that this is precise n squared here. And so I think one can do this, yeah. It shouldn't be too hard, I guess. Yeah. Maybe let's go. You mean this one, right? Yeah. No, I didn't use it. But it was used, that's why I stated it. It was used for the Strichartz estimate on the irrational torus. And also, maybe this connects to the question of Herbert Koch. If you want to have something irrational here, then you also, I think, you also, at least you can go back to this one, to this equation, because you don't have this factor. This factor looks a little bit different on the irrational torus, and so you cannot use this, but you cannot. You can get rid of this factor and then use this estimate. It's also a very simple trick, but very powerful that Bourgain used to prove the Strichartz estimate on the irrational torus. It's really worth reading through this argument once. It's very nice and very powerful.